And chapter 4 is also going to clarify the first portfolio assignment question. It is on the Fibonacci sequence.
Quick question, what was page 2 again?
I don't remember. We're going to have to do it later. So it's over. We've moved on. Otherwise, we never get anywhere. Okay. So, Fibonacci, as he's known now, that wasn't his original name, in the 12th century was very important for bringing the decimal system to Europe. And he wrote the first book in 1202 explaining how amazing counting in tens can be. Getting it from the Hindu and Arabic nations. It wasn't really in Europe. They were all Roman, I guess, still at the time. But realizing the benefit of the decimal system, basing it on 10, is probably his greatest contribution. And when many scholars read his book and his explanation and his demonstration with examples and all kinds of things, they realized, yes, this is the way to go. And here we are today, thanks to him. In his book, chapter 12, he had this interesting question. I'll just show it in the book so we read it together. Let's read from the book. How many pairs of rabbits are created by one pair in 1 year? Question. A certain man had one pair of rabbits together with a certain enclosed place, and one wishes to know how many are created from the pair in 1 year when it is the nature of them in a single month to bear another pair, and in the second month those born to bear also. That was his words. Very confusing words. When you read a solution on the next page, which we won't do, it doesn't get any clearer. So let me just clarify what his question was. Now, it doesn't have anything to do with his decimal system introduction, but it has everything to do with chapter 4, counting rabbits. So he counted pairs of rabbits, but it could also work if you just focus on the female rabbits, which I find a little bit easier. So here are the rules. Things change every month. So every month, we want to have a number of female rabbits. I know it's probably sacrilege that I'm not doing it exactly how he did it, but I find it a little bit easier because it's not super realistic. It's a simplified model of how the rabbits grow, but that was his question. So you start with 1. You start with 1, bang, there she is. Now, there are other males around her. It doesn't really matter. Okay. There's always enough males to do what needs to be done. You have to start with 1. But she's just a baby, so it takes a month for her to grow up enough to be able to have her own babies. So this is month 1. Month 2, she has now grown up. And only now is she ready to have her own babies. So there's a little bit of delay in when she can, there's a month delay in when a rabbit can reproduce. So then, month 3, she always produces 1 female rabbit. She is never going to die. All the rabbits are just always going to live. And now she is creating 1 baby. Okay. So the first one is the original rabbit. The second line there is the baby. Let's maybe highlight this. Go back. OG.
Oh yeah.
And baby.
Perfect.
Now, maybe OR, original rabbit. Now, she can produce one every month. So, she is still there. She is going to create a second baby. And this original baby needs to now grow up. What shall we call her? She's not a baby anymore. She's an adult. Baby 1 is now an adult. Does that make sense? Try to make this as easy as possible. Okay? So, moving on to the next month, she is still there. No rabbit ever dies. Her baby, baby number 2, now grows up to adult. This, oh sorry, let me just backtrack 1 second. I don't have enough, I just need to make space for myself. A little wider here. She's over there. She is an adult, so she can have a new baby. The baby number 2 can't have any babies until she grows up to an adult. This adult is still there and gets a new baby, the 4th baby. Though it doesn't really matter what the B's are, we're going to drop the subscripts. Doesn't really matter. It only matters how many in total there are. How do we feel about this? Just want to go slow enough so it makes sense. Remember, everything I say today is testable on page 5. So pay attention. But nothing outside of what I'm saying and what's written down. Month number 6. We just want to do enough so we can see how this works. Maybe 1 month at least. So I still have the original. Let's make her an adult. She is an adult, so she can have a baby. This baby needs to grow up to an adult. Can't have babies yet. This adult is still there and can have a baby. This adult, number 1, is still an adult and can have another baby. And this baby, number 4, needs to grow up. What?
It's good. It's just a lot of babies.
No, absolutely. It's rabbits. What do you expect? So, if I now keep track of how many rabbits there are, female, rabbits there are every month, I get 1, 2, 3 rabbits, 5, 8. Do we see a pattern or do we need to do one more?
1, 2, 3, 4, 5, 8.
Do we see a pattern or do we need to do one more? One more? It's just a little tricky because that one more can get very confusing as well. All right, let's do this thing. Adult stays an adult. Adult has a baby. Baby grows up to adult. Adult stays an adult. Adult has new baby. Adult stays an adult and has a new baby.
Can you show the numbers on the side?
I will when I'm done. Yes. 1, 1, 2, 3, 5, 8. Baby grows up. Adult stays an adult, has a baby. Baby grows up. Adult stays an adult, has a baby. How many do I get? Should be 13. Otherwise I made a mistake. 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13. All right. I don't want to do another month, so we're going to have to see a pattern.
I think I get it. It's like, I don't exactly know how to say it, but like when you get like 5 plus 3, so like the term before,
Yep, exactly.
then you get the next term.
So the pattern is to get any of those terms, you add the previous 2 together. To get 8, you add 3 and 5. To get 13, you add the previous 2, 5 and 8.
I see. That's okay.
You don't have to really understand, well, oh, obviously it's the previous 2, but yeah, it comes from the rabbits.
Wait, what do you do, sir? I was
To get any term in the sequence, you add the previous 2 together. So that means the next one's going to be, feel free to verify it with rabbits. The next one's going to be 20, oops, that was, oh, there's my pen. 21.
Yeah.
So let's maybe right here, this is called now the Fibonacci sequence. But it wasn't until much, much later. 1, 1, 2, 3, 5, 8, 13, 21, and then 34, and then 55, one more, 89, and it just keeps going, right? Fibonacci sequence. Now, feel free to read his explanation at the top of page 26, but in that language at that time, it's a little hard to keep track. But he did solve it, as long as we see the pattern. Now, can we explain that pattern with a recursive formula? Now, because this sequence turns out to be really special, we're not going to use an A, we're going to use an F, for obvious reasons. Recursive formula. F1 is 1. Because I'm going to add up the previous 2, I need to know the first 2 terms before I can start the loop. And if I want to find the term in position n, I add up the one before to the one before that, the previous 2. How does that feel? It shouldn't be overly complicated, given our background in the last couple of weeks. Understanding that recursive formula should be perfectly fine, and we can certainly explain that by way of rabbits if you really want to. Unfortunately, the explicit formula is not something I can explain. Maybe 4th year math, maybe. But it's not, unfortunately, as easy. Deceptively difficult, actually.
Square root of 5 doesn't look pretty.
Give it time. It's going to look better and better. So, that doesn't mean we can't look at it. But it is interesting in its own right why the recursive formula is not that hard to understand. Add up the previous 2. It doesn't even have any adjustment of them. But the explicit formula for the term in position and just using the position is unfortunately much more complicated. Don't ask why, because I can't explain to you why. If you ever get to discrete math in 3rd, 4th year, it's very nice. But there's a lot of tools you need. We can still look at it and use it and see, well, what is root 5? Square root of 5 is a non-terminating, non-repeating decimal number. irrational. Yet, so that's in the formula. Yet, every number that that formula creates is a whole number.
Yeah.
So let's just find a couple to convince yourself. It's exercise 4.1 anyway. Now we've already found a lot of these, and we're not gonna use the formula for all of them. I just want to use the formula to find the 10th one. How many do we have already? Let me just make some space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these, you can verify them, but I'm not going to use this formula for all of them because we already found a lot of them. How far do we get? 1, 1, 2, 3, 5, 8, 13. Oh, you got pretty far. 21, 34. Let's just use the formula to verify that that one is 55. This is where you take out your calculator or your calculator app or whatever and see that calculation is not, don't look at me like that. It's the formula, it's not my fault. But it's amazing how, I mean, you can do it now, you don't have to. There's no need to throw stuff. I know you don't want to. But do verify that even that ugly-ish formula with the square root of 5, which is not even close to an integer, in combination produces an integer. How on earth could that possibly be? But it is. It is. I don't want to take too long on that, but do attempt the formula at least once and see that you get a 55. A lot of brackets and a lot of stuff happening. So perhaps you don't want to do it right now, or if you're watching the video, pause the video and try. But we can't pause real time. So in the interest of saving time, we will move on. But do verify, I get 55, even though it's a little ugly. Can I memorize that? Yes, I just did. Easy. And there's a lot of symmetry there as well, right? 1 plus root 5 over 2, 1 minus root 5 over 2. And then the root 5 is at the bottom. So it's not that hard to remember. Everything I'm saying today is testable. Now, there are some interesting patterns in the Fibonacci numbers. Some more interesting than others, but I just want to illustrate
That's
some.
what we have a test, the Fibonacci.
I said what I said.
I got
Everything I wrote down on the screen is testable. So, if you look at the Fibonacci numbers and you look at the ones digits, it's not the best pattern, but it is a pattern. The ones digits repeat themselves. You have to go pretty deep. You have to go to 60 of them before they start making a loop of 60. The tens digits loop in 300 length. Every 300, the tens digit repeats itself. The hundreds digit repeats every 1500 times, and so on and so on. It's a little extreme, but there's a pattern there. Another pattern. Let's zoom in one more. This one, I can't wrap my head around why this would work, but it does. Every third Fibonacci number is divisible by the third Fibonacci number, 2. Every fourth Fibonacci number is a multiple or is divisible by 3, which is that fourth Fibonacci number. Every fifth one in the sequence is a multiple of 5, which is the fifth Fibonacci number, and so on. So every kth Fibonacci number, if you go and make jumps of size k, they are all connected to that first one, even though we are never multiplying. We are only adding weird things together. This is the more important one. Sorry, I have a little rabbit in my throat. This is the more important one. Now, it looks much worse than it is. What it says is, if I add up the squares of the first Fibonacci numbers, it is the same of the product of the last two. Well, let's assume that makes zero sense to you right now. Let's draw a picture. Pictures are so nice. Let's draw a picture. I'm going to zoom in. I'm going to make a little, actually I have a square drawing tool here. Let me backtrack. I'm going to make a little 1 by 1 square. 1. Then, just so I orient this the same way, next to it I'm going to make another 1 by 1 square. Try and make them as equal as I possibly can. Zoom. Then on top of that, yes, on top of that, I'm going to make a square, which will then, of course, be 2 by 2, right? I'll put a 2 inside. 2 by 2. Then alongside that, I'll make a square, which is going to be 3 by 3. Then below that, I'm going to go around like this. Oops. Then below those, I'll make a square, and that square is going to be not 4, 5. That's okay, you were just checking if everyone's paying attention.
You're doing good, Josh.
Then on the left, I'm going to make a square, which is going to be 8 by 8. Everyone happy with the 8? Why it's 8? Right? 2, 1, or 3 and 5. Okay. Then I'm going to make a square at the top, and that's going to be how big? A little too big for my screen. That's a little flat, but it's going to be 13. I need to zoom out. Then I'm going to go and make a square again, and that's going to be whatever the next one is, going to be 21. No deep sighing, it's cool. Then I'm going to make a square again. Oop, I need way more space than that. They get really big really fast. Well, sort of. Square. There we go. That's going to be 34. What are these numbers? These are the Fibonacci numbers. Because that's how I'm going to get the Fibonacci numbers. So, if I want to add up the area of all of these, what would that be? That would be the little 1 square, 1 by 1, another little 1 square, then the 2 by 2 square, then the 3 by 3, then the 5 by 5, then the 8 by 8 by 8, then the 13 square, then the 21 square, then the 34 square. But if I look at the big rectangle that shape is, what are the dimensions of that rectangle? Width is 34. Length is?
55.
And 55 is the next Fibonacci number. So if I look at that, that is what they're trying to say here. Fibonacci rectangles. If I now go a little further, because why not? I need to zoom in a lot. And I draw little half circles. Not half circle, quarter circle. I do have another color. That's an awesome idea. Quarter circles. and connect that quarter circle with this one. Oops, that was not the best quarter circle. Maybe a little wider. And then another quarter circle like so. And then another quarter circle like so. And then another, whoopsie. It's easier for me to go from the bottom for some reason. Quarter circle. Oh, that's not very good. Wide turn. Wide turn. Not bad.
So if we can't draw circles.
This is just me driving in the snow.
Whoopsie.
It's not bad.
Hey, not bad is you made it here, so it's good
That's
enough.
not a half. Whoa.
It's a quarter circle. It's my best attempt, okay? And then you can continue, but now my wobbliness will continue as well. So let me just show you. Images can be found on the internet. Fibonacci spiral. Then if you overlay this to the Nautilus shell, it is near perfect.
Yes.
Near perfect. So, the Fibonacci sequence somehow is some sort of optimized way, optimized design that nature automatically figures out. More occurrences. If you look at sunflower seeds, for example, among others, I'm specifically talking about sunflowers. And you see they are, I have a little cough. They have these lines that they're making, curved, but still. If you count those lines in one direction and in another direction, you get Fibonacci numbers. Why? No one knows why. Then if you keep looking in nature, it's not everything is Fibonacci number, but it keeps coming up more and more. There's something optimal about these numbers that automatically happens in nature. Your portfolio assignment task is to find 2 occurrences of the Fibonacci sequence in nature other than the ones I specifically mentioned. So not the Nautilus shell, not sunflowers. 2 others. So you go outside, you take maybe not right now, but you take a photo, you take a video, do whatever you want to do. 2 occurrences, maybe with yourself in it, so I know you didn't just take it from Google. Okay, here's another interesting thing. This is supposed to just be interesting. Why are these things in nature? Why? We are a part of nature. So when, I'm going to do it this way first. When we look at a painting, for example, when we look at art, some things are more visually appealing than others. Why some art is more popular than others. For example, if I make a painting,
Art. Beautiful.
You know, that's my painting. I make a painting. If I make a square painting versus a rectangular painting versus a thin rectangular painting, some of those are more appealing than others. Here's my painting. Now let's suppose I draw a boat on the water. I'm going to go blue. I know I practiced this. If I draw the sort of the horizon over here versus way down here versus somewhere over here, some of those are going to look way better to us without us knowing. We just know that looks good, that doesn't look good. And then if I draw a little boat, which color should the boat be? Let's go back. If I draw the boat in the middle versus on the end versus, I'm just eyeballing it over here. That one's going to look way better than all the others. Why? So what's happening behind the scenes is what we call the golden ratio that many artists have realized is our preference for saying something is pretty and something looks good versus not. So the golden ratio is, it's a little confusing perhaps for some people. If I make two lengths, A and a B, they have a ratio, this ratio, A to B, A over B, the ratio when I divide the small into the big. It's the ratio. I say that is the golden ratio if the ratio of A to B is the same as the ratio of the total length to the long one. That's why I'm trying to go slow so everyone can understand. So first of all, we need to understand what ratio means. Ratio is another word for fraction, which is another word for division. So the ratio of those two sides, those two lengths, A and B, is the big one, the small one divided into the big one. So A divided by B. So the ratio is A over B. This A over B. Okay? Ratio. If that ratio, that answer that I get, if that is the same as the ratio of this total length, A plus B, to the long A length, this, then we say the A and the B are in ratio according to the golden ratio. Now if we do some math, we throw some math at it, we get that the golden ratio is 1 plus root 5 over 2. So people like Leonardo da Vinci realized that that is what we find appealing. This weird ratio, 1.618, that never ends. That is the most appealing ratio. And he used it in many of his works. Now, this is sideways. The golden ratio sits over here. This length to that length. So it's sort of cut in halves. There are two of those rectangles on either side. But they're used in framing the face, the hairline, and also deciding where the eyes sit and how long that neck portion is and where the hand sits. And all those things we don't realize, but when we look at it, instinctively we know it looks good. If that wasn't according to the golden ratio in how it fits in the frame, it would not look good. We would find something else that looks good. This one is called the Vitruvian Man, one of his earlier works. There is the golden ratio sits, for example, right there. How far down his chest goes to his belly button, his forearm and hand ratio. That is what is sort of instinctively, when you look at it, yes, those proportions are fitting, looks good, and so on. So now, and there are many other examples. You can Google it a lot. So now when we look at the formula, the explicit formula, where was it now? Over here. That is the golden ratio right there. And you can rewrite it so the golden ratio is sort of in the second part as well. So the Fibonacci sequence is connected to the golden ratio, to this optimal design that we see in art, that the Greeks used in their structures and their buildings. You can look for Google images, all golden ratios, all Fibonacci sequences behind them. And the ratio of consecutive Fibonacci numbers, like 3/2, 5/3, 8/5, and so on. If I go far enough, they get closer and closer to this golden ratio. Everything's connected. We're a part of nature, so what we feel looks good, is visually appealing, is built into us. And we don't know why, but it is connected to the Fibonacci numbers.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.